let's consider those gases that do not have ideal behavior or are not perfect gases. We call them real gases. They exhibit non-ideal behavior. And there's a couple of different reasons for this, but it's predominantly that there's either attractions or repulsions between the molecules, or the particles themselves have appreciable volume. Those were the two stakes that we said a perfect gas, an ideal gas, would have such an insignificant volume in comparison to its container that we would never have to adjust our volume term to account for the fact that part of the volume of the container is taken up by the gas itself, and that our particles are free to move past each other. They exhibit Newtonian physics, classical physics, and they don't attract or repel. Okay, so this is most likely to happen when temperatures are low. When temperatures get to be very low, you get the particles slow down. They're more likely to coalesce at low velocities. Particles approaching each other are more likely to interact. At very low volumes, you have the potential to have a high pressure. These low temperatures and high pressures, low volumes, are the places where we're going to essentially have a phase transition from being a gas into being a liquid, where in a gas there's no intermolecular attractions, and in a liquid there are significant intermolecular attractions. Our book calls out this, although it doesn't name it. This is a Born-Meyer diagram, and it says that this axis here, R, is the separation between nuclei in two atoms. So I have an atom and an atom, and when they are far apart from each other, they're attracted. And then when they get really kind of close to each other, they start to repel, because the outsides of the atoms are, that's where the electrons are, and electrons repel one another. So I have a Coulombic attraction and a repulsion here as well. So this is my attractive force, that is my repulsive force. The pink line is the average of those two forces. So this is my perfect intermolecular distance, or in fact, when we think about covalent bonds, that becomes the perfect covalent bond distance. What this basically shows us is that repulsive forces act over a very short space. The particles really need to get close to one another before they repel. But attractive forces operate over a much larger domain. So for real gases, PV equals nRT does not hold. It's not true. This is going to give us access to something called the compression factor. Now, there's this chapter of our book introduces compression very, very briefly. Later on in the book, there's a couple of other things that we can do with it. We can specifically look at isotherms and pull Z from graphical information, and we'll do that too. So the compression factor, Z, is Vm divided by V0m. V0m is the molar volume of the ideal gas. Vm is just the measured, or the experimentally found, molar volume of the real gas. Now, molar volume is the volume per mole. Okay, so when we go back and look at PV equals nRT, V over N, that's our molar volume. Okay, so Vm0 equals V0 over N, which is equal to RT over P. And we can throw that back in, and this is the in-between part right here. We get PV equals RTZ. Okay. Oftentimes that's written in terms of Z, that that Z is PV over RT. Okay. But this is a molar volume. which already has an N in it. Molar volume is V divided by N. So it's not that real gases where N would be, ideal gases where N would be PV over RT. Don't think that real gases is Z over, is PV over RT, because this is the molar volume. Okay, graphically what this looks like is if we plot compression factor. We have compression factor and compressibility. They are slightly different things, and we'll deal with them when we need to deal with them. If we plot compression factor versus pressure, what we find is that when pressure is really low, this is the most likely that we are going to have ideal behavior. So my value of Z approaches 1. This dotted line right here, this dashed line, represents 1.00. That's ideality, because the value of Z is the found value divided by what the ideal, the perfect value should be. So an ideal gas has Z equals 1.00 at ideality. So we'll show you some graphs, and they have all sorts of different skews to the isotherm, but they usually kind of approach ideality at the low pressures, and then they go all over the place at high pressures. Okay. One last thing. If Z is a number that is less than 1, that's most likely due to intermolecular attraction. Probably the simplest way of quantifying real gases is to look at the van der Waals equation for a real gas. It still says PV equals nRT, but now there is this term added to the pressure. It is AN squared over V squared. N is just your number of moles, V is your volume. This is a pressure correction that is due to the attraction between molecules as they pass each other. The values of A for any particular type of molecule are tabulated somewhere. They're in a reference text, they're on the internet, and as long as you're dealing with a known gas, that value of A is known. And then V has a volume correction. It is V minus NB. N is the number of moles. B is this volume correction, and again, it's tabulated. It's somewhere in the textbook, in a reference text, or on the internet, and it just basically says we recognize that the gas that you're looking at has an appreciable volume, and then that just equals nRT. So if you rearrange that just exclusively in terms of P equals nRT over V minus NB minus AN squared over V squared. And if we do that trick where we replace V with Vm, and Vm is the molar volume, is a volume per mole that we used in the previous section, then P for a real gas, let's specify that this is for a real gas, equals RT over Vm minus B minus A V squared over V squared M. Okay, and the fact that this knowledge is 150 years old means that the values of A and B have been tabulated for a long time, they've been tried and tested, and they work. Another approach to get the real gas data to fit is to use a virial equation. Now, the virial equation is a power series. So we're going to take just PV equals nRT, and we're going to add a term to it that will bring our data closer to the observed answer. Okay, so if we plot pressure versus volume at a fixed temperature, well, these are isotherms, so the data in the black line all is at the same temperature. and the data in the pink line is all at the same temperature. So those lines represent isotherms. That means we can plot more than one experiment on the same graph. Okay, so at hot temperatures, we might see this behavior, and at cold temperatures, we see the other behavior. Let's see if we can take the information that we've got and then add some terms to it that will twist our data to actually fit the line. So this is a slightly different approach, but in practice, it's quite similar to using the van der Waals form, because these values B, C, and D, if they exist, will be written down, and they're in a table, and we can use them. Okay, so we're going to add these little corrective terms to our existing formula. This is what they call a good first estimation, a good first approximation, that PVM equals RT. Remember, Vm is V divided by N, so the N doesn't need to be here. And then the expansion of this is, I've got a power series here where I'm going to take this coefficient, this virial coefficient B, and multiply it by my pressure term. And if that makes my data now fit the curve, I stop. If it doesn't, I move on to the next item down in the series, and I find the this virial coefficient, and I multiply it by the pressure squared, and so on, and so on, and so on, until I have corrected the information so that it fits my experimental graph. Just substituting in volume for pressure. This is the form that we often use. Most of the examples in our book are going to stop at the first term. That once you've thrown this first term in there, which is actually called the second coefficient because of that one right there, then the answer is usually close enough. But sometimes you have to go further down the line.